Hello, this video is going to be about using the conservation of momentum to solve problems. So we've learned about momentum, which is equal to an object's mass times its velocity. Some important things about it is that momentum is a vector because velocity is a vector. So if an object has a positive velocity, it'll have a positive momentum, and if it has a negative velocity, it'll have a negative momentum. So if you're moving in the direction you've assigned as positive, you're going to have positive momentum, but you can also have negative momentum if you're moving in the direction you've assigned as negative. Now, we've learned about conservation of momentum vaguely, and this says that if you add up the momentum of every single object interacting, you will get some constant number. So if you have two objects, you would add up the momentum of two objects, but you might have 5 or 6. Every extra object, you just figure out its momentum, and you add it together. You'll get the total momentum, which is some constant number. If the objects collide and exchange forces, their individual momentum might change, but the combined number will not. So maybe these two objects collide. This object starts moving faster, and this object starts moving slower. These momenta will change, but the total combined momentum will not ever change. So we use this to solve problems. Normally, this is how we're going to solve a problem using conservation of momentum. We're going to realize that before and after some interaction, the combined momenta will equal the total momentum. And this total momentum will be the same before and after, even though this might not be the same as that, and so these two momenta might not exactly be equal. The total will be equal, so if this one goes up, this one must go down, and vice versa. So we normally solve conservation of momentum problems using a before and an after equation that are bridged together by a total momentum that doesn't change. I have 5 examples for you. Here's number 1. You have 2 pool balls. There's a red pool ball, it's 0.2 kilograms, and it is initially moving at 4 meters per second. It hits a blue 0.2 kilogram pool ball, which is initially at rest, and comes to a stop. So how fast is the blue pool ball moving after this collision? You have 2 balls, they hit each other, they bounce. Well, the way we solve all these problems is we set up 2 formulas, one for before our collision and one for after our collision. We have the red pool ball and the blue pool ball, and their combined momenta does not ever change. This problem tells us how to set up this before the collision, because it says before the collision, the pool ball that is red is moving at 4 meters per second, and the blue pool ball is initially at rest. So we have all the things we need there. We'll plug in the numbers. The mass of the red pool ball was 0.2, velocity of the red pool ball is 4, mass of the blue pool ball is 0.2, and the velocity of the blue pool ball is initially at rest, so that's 0. So we can figure out the total momentum by just solving this formula. Turns out that the total momentum is 0.8. After the collision, the total is going to be the same. This is going to be the same number before and after. That'll be 0.8. And so we see what we can figure out after the collision. Now the masses never change. That is going to be the same, and that's going to be the same, because they didn't all of a sudden gain or lose weight. We also know that the red pool ball comes to a stop at the end. So the new velocity is 0. So this is the momentum of the red pool ball, and this is the momentum of the blue pool ball. We don't actually know the velocity of the blue ball at the end. That's what we're trying to find. But now we have a formula with only one variable, and we can solve it. This turns into 0, because 0.2 times 0 is 0. So we just have 0.2 times v equals 0.8. You can solve that and figure out that the velocity of the blue pool ball is 4 meters per second. So that's the final velocity of the blue pool ball after the collision. Hopefully it makes sense because they weigh the same amount. And the red pool ball totally stops. So the blue pool ball is just going to get all the momentum that the red pool ball initially had. So it'll be this going at the same speed. Example number 2. We have 2 cars. A 1,500 kilogram car traveling at 20 meters per second, and it hits a 2,000 kilogram truck that is initially at rest at a stoplight. This one adds a little wrinkle. When they hit, they fuse together and move as one object. So after the collision, what is the velocity of this 2-vehicle fused object? Like they hit and they just melt into each other. Well, we're going to use our equations. Before and after the collision, the momenta of the car and the truck combined is equal to the total momentum, which is the same. This one's a little bit different because the car and the truck fuse. Now because we have the same system, it's just the car and the truck, then nobody else came in and hit him. The fused momentum is going to be the same total momentum because we have the same system, the car and the truck. So I'm just going to say that we don't have 2 objects now, they fuse together and they're one object. We can solve this. We have all the information we need to figure out the total momentum before the collision, so we'll just plug in those numbers, the mass of the car, the velocity of the car, the mass of the truck, and the velocity of the truck. So if you do this, you can figure out the total momentum before the collision ends up being 30,000. Now, the total momentum is the same before and after. we can figure out this now, the mass times velocity of the car and the truck fused. We know that the car weighed this much, and the truck weighed this much. So the mass of the combined blob is just the mass of both of them added together. The velocity we don't know, but we can figure it out because now we have a formula on the bottom with only one variable, this velocity, which is what we want to find. So we'll just plug in those numbers and divide 30,000 by 3,500. You can figure out that the velocity of the car and the truck fused together is 8.57 meters per second. What we did was we set up our equations. We realized that after the collision, these two things fused together, but it's the same system, so they have the same total momentum. And we realized that we can get this mass by adding up the mass of the car and the mass of the truck. So once we make those assumptions, we can just plug in numbers and get the answer, 8.57. Example number 3. We have a 0.3 kilogram baseball thrown to a batter, and it gets hit by a 3 kilogram baseball bat that was moving at 10 meters per second. So this is how fast the bat was moving, this is how heavy the bat was, the bat hit the baseball, and this is how heavy the baseball was. It doesn't tell us how fast the baseball was going at the beginning, but let's keep reading. After the collision, the bat moves at a reduced speed of 3 meters per second, so the bat slowed down when it hit the ball, and the baseball moves towards the outfield with a velocity of 20 meters per second. So what was the initial velocity of the baseball? It was missing because that's what we want to find. So let's set up our formulas. We have the momentum of the bat added to the momentum of the ball, before and after. That's going to equal the same total momentum, so this is the same number. Now in this case, we want to figure out the initial velocity of the baseball. So that means probably we have all the information to get this. Because we have all the information in every problem, except for one missing piece, which is what we want to solve. You can't ever be missing 2 pieces. That would be impossible. So you just got to figure out which single piece you're missing and that you have to solve for. So in this case, you want to figure out the initial velocity of the ball. So let's see if we can plug in these numbers. It looks like we know the mass of the baseball and the mass of the baseball bat, so we could put those here. Mass of the baseball bat. We also know the final velocity of the bat and the final velocity of the baseball. So we'll plug in those numbers. We also know, I guess I did this at one time, sorry. We also know the initial velocity of the baseball was, or the initial velocity of the bat was 10. And the masses don't change, so these are the same both times. So we have everything we need, except for the velocity of the ball at the beginning. So we're going to solve for this total momentum, because we have all the information. We're going to plug that in here, and then solve the before formula. So 3 times 3 is 9, 0.3 times 20 is 6. The momentum of the bat and the ball added together is the total momentum, which is 15. So that's the total momentum. It's always the total momentum, never changes. And 3 times 10 is 30. So we got 30 plus 0.3 times v, the velocity of the ball, which is what we want to find, is equal to 15. We solve this. Now 15 minus 30 is negative 15, and that's actually fine. Remember that momentum can be negative if you're moving in the negative direction. And initially, the baseball is moving that way, towards the batter, and finally it's moving that way, away from the batter. So we would actually expect it to have initially a negative momentum, because it's coming towards you, and finally a positive momentum, because it's moving away from you. So don't be freaked out about this. But you do negative 15 divided by 0.3, and you get negative 50. So this is the initial velocity of the baseball, negative 50 meters per second. What we did was we set up this formula right here. We had all the information except for the initial velocity of the ball, so we just plugged it all in. We figured out the total velocity from this after formula, plug that up here, and then now we have everything we need to solve for the velocity of the ball. That was what we did. Example number 4, second to last. You have a 73 kilogram ice skater traveling at 7 meters per second to the east, who suddenly grabs the hand of a larger 45 kilogram skater traveling at 4 meters per second to the west. The fact that they're larger physically doesn't matter because they don't weigh as much. It's not important. Without rotating, the two skaters continue skating together with joined hands. What is the final velocity of the two skaters together? Without rotating, this is just to make it technically, there's no angular momentum. Don't worry about it. What matters here, we'll just set up our formula the same way we always do, is we have the combined total momentum before and the combined total momentum after. This one adds another little wrinkle in that this ice skater is moving to the east, and then this ice skater is moving to the west. We'll call this person skater A. We'll call this person skater B. Why not? So remember, the positive and negative directions of our velocities, they're just arbitrary. We can choose whatever we want to be positive and negative. But if one is going east and one is going west, we need them to be different signs. So one could be positive, one could be negative. I'm going to decide that east is positive and west is negative for pretty much no reason. So the skater going to the east gets a positive 7 velocity, and the skater going to the west gets a negative 4 velocity. I could have flipped that, it wouldn't really matter. So we have our formula that we use to solve every single conservation of momentum problem. We know the mass of skater A, that's 73, so that's going to go there and also there. We know the initial velocity of skater A, which is, oh, sorry, I forgot. These two skaters, they join hands and they move together. So in this case, actually, this is kind of like the car situation where they don't stay separated at the end. They have one shared velocity. So you're going to have a combined skater A and B together. You can combine them now or later if you want. Anyway, we can plug in these numbers. We know the mass of skater A. We know how fast they're going initially. We know the mass of skater B and how fast they're going initially. So we can get the total momentum before they join hands. So you can plug in those numbers. And when you chug through the math, you'll figure out that the combined momentum is 331. And it looks like it's positive 331. So after, that's going to be the same amount, because the total momentum never changes. And then now you can realize that the two skaters are actually joining hands, and they're combining together sort of like the car situation. So you're going to not have two skaters, they're going to virtually fuse together to be one object. So you can imagine that it's just one really heavy person. And we know the mass of this very heavy person. It's just the mass of skater A plus the mass of skater B. That's going to be how heavy this combined blob is going to be. So the mass, you combine it both. The velocity is what you want to find. So that's still a variable. And you just plug through the math. And you can figure out that the velocity of skater A and B together is 2.08. Now it's positive 2.08. I didn't see a negative sign there. And remember that we decided that positive was east. If you had chosen negative to be east and positive to be west, then your answer would be negative 2.08. So the positive negative, this just controls the direction, and it really doesn't matter. As long as you get the number right, and you know which direction was positive and which was negative, you can get the right answer. Example number 5, this is the last one. A stationary 6 kilogram gun fires a .01 kilogram bullet with the speed of 350 meters per second. What is the recoil speed of the gun? Now, I have previously done this by saying that the momentum of one object is going to be equal to the negative momentum of the other object. And you could do that, and that would work. But I want to show you why that's true. The thing that I showed you before was kind of a shortcut, introducing momentum. I can do this with conservation of momentum too. The dual formulas will always work. So let me set up my dual formulas, where I have before and after the interaction. The combined momentum of the bullet and the gun is equal to the total momentum. This is going to be the same no matter what happens. So let me just plug in these numbers. I know the mass of the gun is 6 kilograms. Initially, it's stationary, so that's going to be 0. The mass of the bullet is .01. And the bullet's in the gun, it's also stationary, so it has no initial velocity. So the total momentum of this whole system, when nothing is moving at the beginning, is just going to be mass times velocity of the gun, plus the mass times velocity of the bullet, which is going to be 0. And the total is the same before and after. So now maybe you can see where I got this formula. MV gun has to be equal to negative MV bullet, because you subtract this from both sides. That's how you got that simplified little formula I showed you before. But you can also plug in the numbers. So the bullet has this mass, doesn't change. The final velocity of the bullet is 350 meters per second. The mass of the gun didn't change either. The velocity of the gun is what we want to find. So you chug through the math, and you get that the answer is negative 0.583. So the recoil speed of the gun is backwards 0.583 meters per second. Once again, as a summary, the way that we solve all of these problems is we set up two formulas, a before formula and an after formula. The total momentum is always going to be equal to the same number before and after. So you will always have exactly one variable in this big super equation that you don't know. It might be the initial velocity of one object or the final velocity of another object. Maybe it'll be the mass of one of the objects. Or maybe it'll be the total momentum. But you can solve it as long as you realize that this is one big super equation that we use to analyze momentum transfers before and after a collision. and you will always have one variable. If it doesn't look like you have one variable and you have two, then maybe you didn't realize that these two objects fused into one, and so they should be modeled as just one really heavy object. But I promise you, with the formulas we're going to give you and the problems we're going to give you, you can solve everything by saying that the combined total momentum before and after a collision is the same. Okay, I hope that was helpful.